So normally, if we go back our class 11 concept or class not 11, class 7 concept basically, or class 8 concept, the what is called reductions means addition of hydrogen is called reductions, removal of oxygen is called reductions. Now we'll see such example that we'll never think that example previously as or never consider those example as a reduction. This may be the reductions. Okay, and we'll use the very popular chemistry there. I mean, well-known popular chemistry that you read almost every day. Let's think we have a ethylene oxide. So if we use phosphine here, PPH3, what will happen? We know that phosphorus has strong desire toward oxygen, strong tendency towards oxygen. So it will remove that oxygen. Plus PPH3, P double bond O. So basically, see, these phosphines are removed from oxygens, means that this moiety is going to be reduced to alkene. So this is also on reductions. That is, this is going to reduce. Here are the reductions. Let us see another example, same category. During the heterocyclic chemistry, you have studied that this is the inoxides. Again, if inoxide is treated with PCl3, what PCl3 do because of same chemistry that phosphorus has strong desire or tendency towards oxygen. This will remove this oxygen. So we have this pyridine plus P PH3 P double bond O. Similarly, this has been reduced reduction. So why I have started from this because these are the example that's we frequently use, but we very tricky. We do not concentrate on put concentration on them that this kind of oxidation reduction is going to happen very nicely, and we no need to discuss about that electron transfer. This kind of uh, some deep discussions, but rather just class 7 chemistry, removal of oxygens means reductions. So it is simply removal of oxygens. So if a question is given, which is the oxidizing agent here, then PPH3 is the oxidizing agent. If some, okay, then let's see this one. So here we'll used, now we come back to our normal examples and slowly we'll go into read deeper and deeper part. So H2PDC. Basically, this is a chemoselective reducing agent. Reducing agent. Why chemoselective? Let us think about the following examples. So we have two reducible group. One is aldehyde, another is the alkene. If we treat this by H2PDC, CHO, and this group is going to be reduced, not this aldehyde. That's why this is chemoselective. One thing, though it is irrelevant, but again I am telling that this paradigm carbon, when we will do your research, when you use this thing, this is very much tricky to handle this. Lots of time catches fire. So just for information means. And we have to take care of a lot of things during the reduction also. It's not only that we put H2 paradigm and it is going, it's not like that. We have to take a lot of precautions. Okay, that is not our part here. We can go back to these things. See, we'll use different use of paradigm charcoal here. For examples, we have these things. Cyclohexanone. You want to install one NH2 here. Then what you will do? Previous day, we have understand or we have read this chemistry. If we put nitrous acid, this is going to be double bond NOH. Now the role of H2PDC come. H2PDC. double bond O and H2. This is highly interesting. Another thing that now quite a modification in the catalyst H2PD instead of charcoal, we're using calcium carbonate or lead acetate. PbOAc equal to, and also you can take calcium carbonate. These are quite different things. We'll not discuss here. That's a little think about these things. But they do. This is methyl. If we use these catalyst combinations, we'll have cis diene, not diene, cis alkene. Later we will see, and there are how many ways that we can synthesize these things. Basically, what happens is this. This is the palladium surface, PD surface, and here we have the hydrogen first attached with the substrate. Then what happens? In this way, the active hydrogen forms, and as this active hydrogen forms, then the hydrogen is transferred to the, let's say this is the alkene substrate or alkane substrate. It transferred from the same side, same side. It's transferred from the same side. That's why we get always cis alkene. So we are not just have a look on this. Why it happens? Hydrogen gets absorbed on catalyst surface, then it cleaves, it's produced reactive hydrogen. This actually transferred to the substrate size from the same size. So if you have a methyl group that will bend this side, if you have another methyl that will bend this side. That's why we are getting this cis alkene. Okay, let's do. Let's say we have these things. We want to convert these things. So if you want to rationalize why this is called reduction, see, this carbon is losing oxygen and gaining hydrogen. So from that point of view, if we consider from the point of view of losing oxygen, that is called reduction. From the point of view of gain of hydrogen, that is reduction. But how to do it? So here we use an efficient multi-step process using some interesting carbonyl chemistry. Look these things. BF3. So what BF3 do? BF3 activates its functionalities. It acts as Lewis acid. So then we have these things. This six-member thiacetyl. Basically, what happens? Again, okay, we will not discuss that part quite apart. Now we'll focus on our side, what we're going to discuss. On this complex, if we use Ranny nickel and hydrogen, then this linkage is going to break. And this will be Me. And this moiety is very much interesting moieties. Means later we'll discuss in some different classes that how this moiety is used for the reverse flow Ampulang, why this moiety breaks in presence of mercury, and why this moiety is stable. Basically, which kind of delocalization, which kind of charge means which type of electron transfer. This is we discuss later some different dedicated classes. Yeah, here I will incorporate one more interesting reducing agent, that is this H. So this is called diimide. Diimide. So this is very fantastic hydrogen donor. It's a good hydrogen donor, good H donor. So if some question comes in some different way, will not be confused and be worried about that. So how does it work? Let's say we have this alkene, we have this N double bond N. Uh, I put it in this side. Yeah, and there is a four-member ring formations after that. C double bond C. Here we have hydrogen and nitrogen. Then what is happening? Yeah, alkene is going to convert into corresponding alkane plus nitrogen. Okay, so let us think. So basically, this diamide is a good hydrogen donor. Then, if this is given, these things in presence of hydrogen, or NH2, NH2, what we can write H22, then what will happen? The things is that hydrogen in presence of H22, it forms that diamide H2N NH2 plus H22. Then it forms these things. Basically, such type of questions means they are indirectly telling you are treating this compound with diamide. So basically, it's equivalent to treat these compounds with diamide. So NH2 hydrogen H22, or now we know that this diamide forms after the in situ reactions. Basically, what will be? It will convert to an alkane. Okay, let us think about these things. So this has been given hydrogen, it has been treated with these things C2H, C2H. Here just we have taken the methanol solvents and at boiling conditions. What happens if you treat these compounds at heating or boiling conditions? It produces diamide. So no need to worry about these things. So no need to get fear also. This is given. It means that you are allowing the reaction to react with diamide. So what happens? This double bond will reduce to single bond. So hydrogen, hydrogen, CO2H, CO2H. And here this diamide plus will have 2CO2 as 2 carboxylic acid decomposes into 2CO2. This chemicals means diamide, yeah. So H2H N double bond NH. This is a chemoselective also. Chemoselective. How? Let us see the following examples. So we have these things: double bond O. You treat this with hydrogen As it is hydrogen, so we have to use a peroxides. So it generates a diamide that reduces this double bond. We know diamide reduces the double bond, do not reduce carbonyl. So from that point of view, it's a chemoselective. Okay. Then slowly we'll start discussing different other chemoselective reagents. Lithium aluminum hydride. Yeah, I'm just quite anxious also because this kind of reagent, honestly speaking, the beautiful, marvelous chemistry exists inside the reagent. One reagent will take at least 3 or 4 classes, at least, for the perfect discussions. But yet, we have to proceed. So what it does, it reduces different kind of functionalized carboxylic acid to corresponding alcohol, ester to corresponding alcohol. Just for simply, let's say you have RCOOH, lithium, aluminum hydride. I strongly believe every student knows these things. H. Then it's not these things. We'll take different substrate. R C double bond O OAT. If this is a ester H4, then it will be R CH2 OH. If we have acid chloride RCOCl LiAlH4, it will be R CH2. Basically, what happens is the hydride it reduces by hydride donor. Yeah. Now we'll come to the part. Let's say we have these things, these epoxides, and if you treat this with the lithium aluminum hydride, what will happen? Then one hydride will be transferred from these things, H, Al, H3 minus. So this will be transferred. So this will be transferred from which end? From the less sterically congested end. So this end is sterically congested. It will be just hydride will be transferred to this carbon. So as a result, we will have this alcohol. And what is the role of this lithium? Actually, lithium basically coordinates with these oxygens and activate this epoxide basically. This type of coordination happens with this lithium. Just I'm touching in this very through very small discussions. Li plus and something have a some positive charge generates. So this become quite electron deficient species. And as hydride is electron rich, why hydride electron rich? Basically, it's attached to a metal. That's become highly positive. That's why it leaves their negative charge corresponding to the hydride ion. That's why it will happen in a quite faster manner. That's I discuss very simpler way. So basically, what is this? This is very strong reducing agent. Strong reducing agent. Because look the charge of aluminum. Basically, aluminum 3 plus. So the hydride is attached to a highly electropositive metals. That's why H will be released very faster. That's why it's a very strong reducing agent. So here the metal hydride bond is means Al, basically a plus 3. That's mean this bond is highly polarized. Highly polarized. That's why H must be donated in very faster way, faster donation. That's the reason behind why lithium aluminum hydride is a very stronger hydride donor. In comparison to sodium borohydride, NaPH4. So here hydride is correlated to boron. Boron is not that much electropositive. Basically, there is no comparison between the electropositivity of boron and the aluminum. Aluminum is much more electropositive than. So using that concept, so it will be milder reducing agent as than lithium aluminum hydride. As if you just consider this bond is less polarized than HAl bond. That's the logic. Now we'll treat the same compound, one with lithium aluminum hydride, one with sodium aluminum hydride. We'll see what will happen. Look, very interesting. CO2H. We treat this with lithium aluminum hydride. So what we'll get? This will be OH and it will be CH2H. So if we treat the same compounds with sodium borohydride, then what will happen? Sodium borohydride being a mildly reducing agent, it only reduces this carbonyl. This will only reduce this carbonyl OH. As between carboxylic acid and the carbonyl is much more reactive than carboxylic acid. Okay. Then we'll find two properties. Means if true false is given, then I have to choose something. So it reduces the carboxylic acid as well as the carbonyl. So it is non-chemoselective. Lithium aluminum hydride is non-chemoselective, whereas sodium borohydride is chemoselective. Chemoselective. Second, look at examples that let's say we have these molecules. Double bond O, yeah. We're treating this with lithium aluminum hydride. Now what will happen? Now we know that this is non-chemoselective, which will reduce both the carbon as well as this is both the carbonyl. So this is quite unreactive carbonyl, as this is alpha beta unsaturated and this is reactive carbonyl, but is very much stronger. That's why it reduces both. But what happens? The same chemicals, same compounds with sodium borohydride. Now we know that this is a chemoselective reagent, so it will reduce to the reactive carbonyl to alcohol, not the this one. Why this is unreactive? Yeah, this is alpha beta unsaturated carbonyl, that is unreactive. So again, chemoselectivity is reflected by sodium borohydride. Really? Chemoselective. Next. Now to see this bond is highly polarized. This bond is highly polarized compared to these bonds, less polarized. Then, as it is highly polarized, then it will be decomposed by water, decomposed by water or polar protic solvent. Polar protic solvent. So, when we will use lithium aluminum hydride, what we have to use? We have to use like THF, ether. We have to use ether as solvent, THF, and this is soluble in polar solvents. So this is not soluble in ether because this is this bond is that much polarized, so it will be soluble in polar protic solvent. Okay. Now using these things, we'll see a fantastic reaction. So things this is plus. So if we treat this with lithium aluminum hydride, what will happen? Aluminum hydride. So it will H minus that produced from lithium aluminum hydride and going to react these things, and we will have N. Yeah, this is the product here. But if we do the same thing with sodium borohydride, then what is happening? Here also hydride will attack these things. In this is the initial thing. As we have said, you cannot use this reagent with aprotic solvents. In the system, you have polar protic solvent. Let's say it's a ethanol. You have used ethanol. Then what will happen? So again, further this kind of reduction will take place. Means hydrogen addition to the ring will take place. So as a result, what? This is nitrogen plus, and here we have hydrogen. And what will happen after that? We have hydride in the systems. The hydride will be reacting these sides, and we will get these things. So one fantastic phenomenon has been happened here. What is that? Throughout the up to this thing we discussed, lithium aluminum hydride is strong reducing agent or stronger reducing agent than lithium sodium borohydride. But here lithium aluminum hydride reduces only one bonds because it have to be used with polar aprotic solvents. Means THA or non, it's quite aprotic solvent. That's why further reduction do not proceed. It is the solvent system that drives the reaction. But here, though sodium borohydride is a less reducing agent compatible than lithium aluminum hydride, first it reduces this, and second time because of the solvent, the second reduction is initiated as well as takes place. So this is more reduced product. A weaker reducing agent is reducing at greater extent. That's the beauty of chemistry. It's more reducing. I shouldn't say more reducing. Extent of reducing is more. So extent of reducing is more. Extent of reduction is more. Here, extent of reduction is less. So, who is the villain here? It is the solvent that is a villain that is making a less mean a reagent having less reducing ability or power, making is more. So solvent is the main villain here. So here solvent is the hero that makes the less reducing agent is more powerful at that particular situation. Earlier we have seen if we have these things using H2, palladium, lead acetate, and calcium carbonate, we got this cis product. We try to get these cis products in some different manner. So that's why we'll use the boron chemistry. Boron chemistry. This is highly important. Not only important, highly interesting also. So what happens? Let's see it. We have this alkyne. We have treating this with a bulky boron derivatives. B2. Then what will happen? We'll have a four-member ring formations basically here, and just I should show it indifferently. Will not show it here. Yeah. C double bond C H Br2 is a four-member transition state, and ultimately C double bond C. We have a H here, and here we have Br2. So in presence of acetic acid, so this will be converted into corresponding alkene. Methyl, methyl hydrogen. So we got this is one method to produce these alkenes. This is another method. And I believe you know very much both of these two. Then another fantastic chemistry of boron. Let's say we have this amide, NMe2. We use BH3 and just then we will hydrolyze this complex. This will be NH2. So boron provides hydrogen to this carbonyl and reduces it to not NH2, it will be NMe2. This will be NMe2. Okay. BH3. Then what will happen in place of BH3? So first, what happens? The boron is electron deficient. It's 6 electron systems. As boron is electron deficient, it acts as, so basically let's H is here and this is H2 Lewis acid catalyst, del plus, del minus, and then the hydride is transferred from this side to this carbon. As a result, here we have hydrogens, BH2. Then if we hydrolyze this intermediate, it will be H. Here look, the boron is very peaceful guy. He is very much peaceful. It always likes the position which is less hindered. So this site is corresponding less hindered. This is less hindered site, less congested. I should say not hindered, less congested. That's why boron is coming to these sites. Boron is always remember boron is very peaceful guy. He's always likes a position where steady crowding is more. So with the same concept, we come to this chemistry. Yeah, we have given BH3. So what will happen? Yeah. So hydrogen will be transferred from these sides, and this is delta plus, delta minus. So boron will come to this end. So it will be, yeah, just I'm not showing the stereochemistry, but rather here I am showing it. Hydrogen, this is OH2 and H3O plus. We have to always remember careful about the stereochemistry or stereochemical position of different functional group. This is very VVI and interesting, the role of boron. So we always will always prefer less hindered site. Less less hindered site. And the CMR the statement. Boron is very peaceful guy. We always go to the less hindered site. So let us come with a real example. As I said, this is methyl, this is methyl. So we have huge C5H11 in dice alkyl substituent BH. Then hydrogen, methyl, methyl, C5H11 whole 2. Then H3O plus, sorry, this is H. The beauty of the reagent, so it restrict the further reductions as it has only base. So it has if it was pH3, then it would have two more hydrogen. It could be used that two hydrogen for further reduction. So it doesn't happen here. Every example for boron chemistry is fantastic. If I put on giving or keep on practicing or keep on providing the example 50 example boron chemistry, you will enjoy that 50 examples. Is that much interesting. And one question from bone question normally comes in almost every competitive exams. Let's say these things. So what will happen? C5 H11 equal to BH. We have two double bond sides, but as this is a bulky boron derivative, it will always prefer the less hindered sides. So it will come selectively from these things. So it's a chemoselective. It's prefer terminal double bond. Terminal double bond. So we have these things. C5H11 whole 2. After this, just process it by CH3 CHH, it will be H. So this is chemoselective. Chemoselective. So come to the next part. Let's say we have this methyl and we have treated this by base 3. So among these two sides, this is less hindered side. So first boron will attach with this and the hydrogen will be transferred to these sides. As a result, this is BH2 and this is H. I am not showing there. You know already this. If you treat this with H2O2 and base, then what will happen? This will be converted into corresponding alcohol. This is alcohol. Now, the another thing. If you heat it at 160 centigrade, then boron has a tendency to become isomerized. So boron will leave this place and this peaceful by guy boron will come to the least hindered side. If you heat it. Base 2. Then just use H2O2 OH minus, it will be, yeah, OH. And here I have done a slip of the pen. Basically it will be these things. Now we'll study the isotopic leveling. Means this which hydrogen comes from which thing. Which hydrogen comes from the acetic acid, which hydrogen comes from boron. That's why we have these compounds. If we treat this with BH3, now we routinely know the boron being as a very peaceful guy, it will come to the less in that site. Now this is hydrogen here. So here if we treat this by CH3COOD or D, now it will be these things. Yes, D. That means this last one is provided by the acetic acid. And instead, if we allow to react with first BD3, then what will happen? So boron donate one hydride to here. So this will be B D2 and here we will have one D. Then treat with again acetic acid. H D. These radio level experiments gives us details about which hydrogen is donated by which entity. Now we have discussed a lot about boron. Now we'll discuss about these reagents. You all know this. Aluminum isopropoxides, CH, Me2, whole 3. What is happens? So this is a carbonyl that we are trying to reduce to whom? So we have to use this alcohol. It's for technical purpose reactions. I am not going to tell details. You know these details already. Then what happens? So this reduces to corresponding alcohol. Sorry. But the students keep patience. At the end of each class, you will have a lot of fantastic information, fantastic. Uh, Also, you will gain some fantastic desire toward chemistry. Also, I am going very slowly because if we go fast, then we could miss a lot of interesting phenomena. So this is the reduced part, and this part will be oxidized. So this is the reductions. I am not showing any mechanism here. I could not resist myself to say you a fantastic phenomenon about this reaction because the reaction was again done by me during my postdoctoral research or something in lab. What happened? Its melting point was like 82 degrees centigrade, and its melting points, not melting points, boiling points. I'm sorry, it's BP. It's BP, and this boils at 50 degrees centigrade. So look, so this is a reversible reaction. So if we could separate or if we remove these things from the reaction mixer, according to last Sutherland's principle, the reaction will move forward. If we could remove. So now what will be the new arrow? These things plus I am not drawing totally this part. The arrow will be to that side if this product is removed. So how to do that? The reaction is done above 50 degrees centigrade and below 82. So if it was above 82, then 82, then this will go away. The reaction wouldn't happen because this has a role also. And if it is above 56, after the reaction, this will automatically go off. So it is in between above 56. So in between above 56 and below 82 degrees centigrade. That's why when I am doing in between, it is going up automatically and it is not going up at this is below 82. As a result, the reaction move to the forward directions because it is following the last life principle, it is going up. That's the beauty of this thing. So, though it is irrelevant part here, but I cannot resist myself to let you know this fantastic phenomenon that happens during the oxidations. And normally it is not discussed normally in books. If you see a very good book, then only you can see these things. Okay, so this is a very chemoselective reagent. So this is what chemoselective. Then what will happen? Let's we have these things. TH, CH, double bond CH, CHO. We have used aluminum isopropoxides, maybe to whole 3. Then it will reduces this to corresponding alcohol, and it will not be reduced by things. CH, double bond CH, CH to H. So chemoselective. Then I'll discuss about sodium cyanoborohydride in a BH3 CN. As the boron part comes, means it's a less weaker because BH bond is less polarized. If something takes time to happen, it will be very much selective. So that is weaker and more selective. Ah. So now let us visualize or rationalize something in terms of our practical examples. Why we can become more selective. For example, let's think about yourself, the students. So you are trying to visit a place, means for holidays purpose or something purpose, four place is option for you. So in a fraction of second, you take the decision, okay, I should go that place. I should go to that place. Then what will happen? You can go any of the four. So maybe because of your quick decision or faster decision, it may be right one. It may not be right one. So more, it could have been that there is some place that would have more cheaper but with better beauty. But it will take your times. Okay, I will think about 10 days. I will ask some different peoples. I will get to know about the places. Then I will take the decision. So when your thought process is being slow, then you will have perfect selectivity for the places. You will go to that places perfectly. Similar things. As the sodium cyanoborohydrates, this bond is weaker, means not the bond is weaker, the bond is less polarized or weaker hydride donor, then it takes time before the reactions. It's a good the molecules run through a good thought process. It takes times. That's why it is more selective. Especially I know where I should go. Exactly there it goes. That's in this way you can rationalize such things from your own experience also. If you have these things, now you have used first BF3. When BF3 use, you have to use corresponding some adapt one. I cannot discuss this that much details here. So what BF3 does, so this increases or activates these epoxides. BF3, this is del minus, del plus now, del minus. As this H-H bond is less polarized, it acts as quite nucleophile here. As this is quite has nucleophilic natures, so this bond has quite nucleophilic nature. Nucleophilic nature. Then, among these two carbon, which carbon is better nucleophile? The carbon that develop a partial positive charge, which can be more stabilized. That's why. See, this is tri-substituted. I should say di-substituted. This is mono-substituted. So this carbon is more nucleophile. Okay, I am not using this logic. This is quite wrong here. So just here, what happened? The hydrogen will come here. I'm just making it clear now. OBF3. So this is nucleophile, but it will act through SN2 mode. So in SN2 mode, where it will go to the less hindered carbon, where the sterical conjunction is less. That's why it will go to this carbon. It is hydride, methyl, then just acidify this or work up this, we will have these things. Now remember what we did. If we had these things, same epoxides, if we had same epoxides, when we have treated with this by BH3, just couple of slide before I have discussed this, then we have, after some workup, what we had these things. We had hydrogen here, we had OH here. Same boron reagent, one look, one OH is here and OH is here. Just by using different kind of boron derivative, more selective, means sodium cyanoborohydride, we have got two different alcohol from same compounds. So basically, in short, we have these things: BF3, Et2O, followed by sodium cyanoborohydride, we'll have these things. And if we use this reagent, BH3 followed by workup, oh sorry, again something is wrong, it will be this OH, and here we have this OH. Just we have to be careful of the reagent. So this type of questions will be asked in many competitive exams. And I'm quite sure in that I discussed in last two class, the oxidation and reduction, it will give a lot of advantage in your exam. And you will remember this when you will just appear in the exam and solve some problem. Okay. Another thing we learn about sodium cyano, that is normally not done everywhere. Let us, this is Br and this is CO2 ET. What I discussed, that this bond, I should write here, in sodium cyanoborohydride, not everywhere. NaBH3CN acts as nucleophile and acts in SN2 manner. Acts in SN2 manner. So what will happen if we treat this compound with sodium cyanoborohydride, NaBH3CN, then on hydride will act as SN2 manner and will replace this bromo. So bromine will be replaced by hydrogen. That is, this is not normally we do. The one rule we add that sodium cyanoborohydride NaBH3CN removes what? Iodo, bromo, etc. So when, just do not get confused. For example, this has been given to you exam and they have used or given sodium cyanoborohydride, just by mistakenly do not make it like CH2H and put it bromo, because it will not done, because this provides hydride in such hydride that acts through SN2 mode. That's the beauty of this reagent, because this bond is quickly polarized. That's why, but rather what it will do, it will replace the bromo. So we have to remember these things. Dear students, again, I'm sorry that there are fantastic things we can be discussed a lot for taking each and one reagent individually. But here it will have a sum of classes. Here we don't have any options here. Okay, let's think about these things. What is the reagent? You know that. He's got DIBAL. DIBAL, DIBALH, or DIBAL, we can say. And what will happen? Let's say we have these alkynes and we have treated this with DIBAL, H, Al, C double bond C, Al. I'm not writing that part, and just hydrolyze it. It will be end up with a alkene. See, now we have practiced three processes of making cis alkene. One, remember, it was by palladium catalysis. Number two was done. One was done by palladium catalysis, PD catalysis. Number two was the heavily substituted BH reagent, and here R was C5H11 whole 2 B whole 2. I shouldn't say R was C5H11, C5H11, and this is the third one by TIBALH. So we'll remember. So anything is given, we should not be worried. Just we'll go for one options. One fantastic phenomenon happened. Basically, it is also very much trio selective, chemoselective. This is chemoselective reagent. Chemoselective means if I these things with then it will reduce this OH, not this alkene one. Last, I will discuss one of the most interesting examples with, yeah. So what will happen? It's a reduction by electron transfer. If we reduce it by electron transfer method, lithium is taken as liquid ammonia. It transfers electrons. So we have to take a solvent. Let's say ether is the solvent. The reaction proceed via electron transfer mechanism. So there is two possibilities. Let's think. So if electron is transferred here, we will have OH here. And if the electron transfer is here, OH will be axial. Between these two things, this is unstable or not stable. This is unstable. So it will not be formed. So it will not be formed. This will form. Again, further electron transfer will happen. Then we will have two electron here, and after that it will be H and H. So the stereochemistry will be these things, not that thing. So in sorry, So if it is given with lithium, ammonia, ether, so this will be weight. So this thing is called, that a name of interesting name. This is called PDC, means product development concept. As this product is thermodynamically controlled, that's why this growth is important. If something controlled, the state approach control, then it will call SSE. We will not talk about that. Here it is called PDC, means product development control. Means during this transition state or during this intermediate, the product becomes stable. So product development control.